All right, I guess I'll start. Um, so today, as you can kind of tell by the title, I'm going to be giving a short lecture on computer vision and kind of what computer vision is, what are the most common applications of computer vision, looking at current times as well as projecting into the future, and then do a little bit of a deep dive into the back end of computer vision models, and then at the end, going to have a short demo of a very trivial computer vision example. So firstly, to start off, what is computer vision? Now, the main motivation behind computer vision is in fact biology. And because we can see, uh, we know that there's an incredible amount of information visually available in the world around us. And that fact has really motivated us to kind of try and replicate this functionality within computers. So whether biological or machine, the objective of vision is really the same. That is to sense our environment, interpret or get sense our environment and interpret or give some meaning to what is being sensed. And this can be easily illustrated by the flowchart seen on screen here, going from an image to some sort of sensing device, whether it be the eye or internal within a computer, like the camera seen right there, the interpreting device being the brain or the actual machine, and then gathering some interpretation of the data that's being inputted, like seen on the right. So to the computer, an image is nothing but a matrix of values, each of which values represents the intensity of each individual pixel within the image. Now, this is normally represented by values ranging from 0, which represents a quote-unquote off pixel, to 255, which represents a quote-unquote on pixel. When processing images, the overarching goal of computer vision is to bridge the gap between pixels, like the ones on the right, and meaning, like what we can see on the left. Now, moving into some common computer vision applications, I have a question for you guys. What is currently the most commercially abundant application of computer vision research? So maybe just leave in the chat some thoughts that you might have. Got OCR, self-driving cars, OCR, image search, Google Images. All great guesses. So the answer is actually right, OCR. And this is usually not associated with computer vision just because of how abundant the technology actually is. But this technology is bundled with virtually every type of scanner available today, like printers, like you see on the left, license plate detection systems for automated toll routes. Those of you who live in Ontario, the 407 uses this. That's why you drive through those big rigs of cameras going onto the highway. Document text applications, and many, many more. So moving on to some more current applications of computer vision, what we can see here is biometrics through sensing biometric data like fingerprints or face scanners, which is widely available in almost all smartphones today. Face detection, also available in many, many different smartphones, either in the camera or through other apps like Snapchat, applying Snapchat filters. And then finally, special effects in movies. All of these technologies are founded on the base of computer vision. Moving into some more future and projected applications, some of the main emerging applications are, like some of you mentioned, self-driving cars, image-guided robotics, as well as augmented reality. So definitely a lot of cool applications coming up in the future for computer vision. Moving on to some of the technical specifications of computer vision, starting with data. What is an image? So images are the fundamental input data of any computer vision model. At the core, images, like I mentioned before, are just numerical arrays. And I think everyone has a pretty good idea of what pixels are and how images are just collection of pixels. In fact, if you look far enough into an image, like you see on the bottom, you can start seeing the discretization of the image, which normally looks smooth. For color images, there are 3 distinct color channels known as red, green, and blue, and these are all overlaid to produce the final color image. And for grayscale images, there's only a single color channel. Next, model selection. So choosing a model for any computer vision task really depends on what computer vision task you're trying to achieve. First, image classification. This is placing images, input images, into specific categories. Object detection, which is identifying specific objects within an image and often wrapping them in either a bounding box or labeling them. Object tracking, which is normally associated with video input, and this involves following a specific object within the video input. Semantic segmentation, which is labeling objects within the input. For instance, if you had an object or an image of 3 cars, all 3 cars would be wrapped and labeled car. For instance segmentation, on the other hand, using the same example, each car would be labeled with a unique label. For instance, if there are 3 cars, car 1 would be labeled car 1, car 2 would be labeled car 2, and so on. However, even though their model selection is based on what kind of output you want, some of the most common computer vision model architectures are convolutional neural nets, which works by applying some filter over the input and extracting features from that filter, and then using those features to intelligently predict what the output is. Residual network, which works very similarly to a convolutional neural network, in fact, but instead uses skip connections within the model to preserve the model weights that you're training. And finally, GANs, which are generative adversarial networks. And these work by layering multiple neural networks which have separate jobs. The first being a generative, which produces output images that are fake. And the second model within the generative network is kind of the check, which compares which checks if the input to the network is one of the fake examples or one of the real examples from the input dataset. Some of the most common computer vision libraries are OpenCV, which is one of the largest open source computer vision libraries available. And I'm sure if any of you have experience with computer vision before, you've probably used this library. TensorFlow, which is just the general Python machine learning network, which you can kind of customize any model you want for any application, and also has extensive computer vision functionality. SimpleCV, which kind of true to its name is very similar to OpenCV, however, is much more beginner friendly and requires much less theoretical knowledge of computer vision to operate. And finally, YOLO, which stands for You Only Look Once, which is a real-time object detection system. Now we're going to move into a pretty simple computer vision demo, just to illustrate to you guys using OpenCV for a computer vision task. So here, we're going to look at this notebook here with the goal of lane detection for a video feed of a camera in a car. So here, importing libraries, OpenCV, as well as NumPy, which is the standard mathematical tool used in Python. A bunch of different function here. Canny, this is the object detection edge detection algorithm, sorry, that is used in OpenCV. This function here determines the region of interest using the edge detection algorithm, sorry, and filling out the region of interest with a certain color so that we can visually see where the computer thinks the lanes are. How lines. This how transform is a feature extraction method used for detecting simple shapes within the input field. This is a supporting function to actually determine where the lanes are within the image. Add weight. This is a simple function to just support the learning of the OpenCV model. Make points, again, another supporting function for the draw points function to actually plot the lanes that the computer sees onto the final image. And then display lines, again, just displaying the lines in the video feed for where the computer thinks the lanes are. So we'll go ahead and run this, and you guys will be able to see that there is a little bit of error in this right lane here, but all in all, the computer is doing a fairly good job at detecting where this lane is in this video feed. Oh, sorry guys, I'll share the right thing here. All right, are you guys able to see it now? Okay, awesome. Sorry about that. So I kind of go over it quickly again. First cell here, just importing the right libraries in order to do the computer vision demo. This canny function here is the natural OpenCV edge detection algorithm. Region of interest is just determining the region of interest using the canny edge detection algorithm, and then filling out that region of interest with the overlay of where the computer thinks the lanes are. How lines, this function basically just is a feature extraction method for detecting shapes within the input field. So this is another supporting function to determine where the lanes are in the image. Adding weight, this function helps in the learning of the algorithm. Make points, again, just supporting function to plot where the computer thinks the lanes are. And then right here is just the learning function. So we'll go ahead and run this here, and you guys will be able to see, hopefully. Actually, I don't think you guys will be able to see this. Hold on. Okay, you should be able to see it now. So once we run all this, we'll get the output here of where the computer thinks the lanes are in this image. We'll run it once again, just so you guys can get a better look at that. Now it's obviously, there is some error within this because it is a pretty simple network that we've used here to do this lane detection. But all in all, it does a pretty good job detecting the lanes when the road is straight. And that's it for the demo. So thanks guys for listening. If you have any questions, you can drop them in the chat now. Yeah, the notebook is available on the GitHub repo. It should be under the computer vision under the data science folder. All right, so if there's no further questions, you guys are free to go join whatever other session you want if you want to catch the end of that. But otherwise, thanks for listening. It was awesome. It was awesome to get to present this here, and I hope you guys liked it.